Today we will be studying magnets and electromagnetism, which is chapter 17 in the physics syllabus. So a property of a magnet is that it has two poles. A pole is a part of the magnet that exerts the greatest force on different materials. So in the diagram, we can see that the iron filings are gathering near the ends of the magnet more. So these two ends are going to be the poles. Magnetic material is the material that is attracted by the magnet, for example, iron and steel. Non-magnetic material is not attracted by the magnet, for example, cloth or aluminum. There are two laws of magnetism. The first one is that like poles repel each other. The second one is that unlike poles attract each other. So here we have three unknown materials. One of them is a magnetic material, the other one is a non-magnetic material, and the last one is a magnet. So we take a known magnet to each of these three materials. The non-magnetic material will be the material that is not going to be attracted to the magnet. Both ends of the magnetic material will be attracted to the same pole of the magnet, and one end of the sample magnet will be attracted to the one pole of the known magnet, and the other end will repel the same pole. Induced magnetism is when we put a magnetic material near a permanent magnet and it becomes a magnet itself. So the iron bar is going to be attracted by the magnet as magnetism is induced in it from the permanent magnet. So the first method of magnetizing a steel bar is the stroking method with single touch. So we take a magnet and we continuously stroke it against the steel bar. We can tell which pole it is because the north pole is striking over here first. This end is going to be the south pole, and since this is the south pole, then this will be the north pole. Double touch method is the same, but you're going to use two magnets. So the north pole will be at end A and the south pole will be at end B. The next one is the solenoid method. In this method, we use a DC current. So when we turn the switch on, a current passes through the solenoid and the steel bar is going to become a magnet. We can tell the poles of the magnet by using the right hand grip rule. So we point the fingers of our right hand in the direction of the current, and our extended thumb will point towards the north pole of the steel bar. To demagnetize an object, there are three methods. The first one is heating, the second one is hammering, and the third one is electrical method, where we use an AC supply. So in the electrical method, we put our magnetized material inside the solenoid. We turn the switch on, so current is passing through the circuit. And while the current is still on, we slowly take the magnet out of the solenoid, and that is going to demagnetize the material. Magnetic screening is that magnetic field lines prefer to pass through a magnetic material. So if we put soft iron between these two poles, the magnetic field lines are going to pass through soft iron. So we can tell that magnetic field lines prefer to pass through the soft iron instead of air, and this is used in voltmeters. So the magnetic properties of soft iron and steel. Soft iron is easy to magnetize and demagnetize and is used as a temporary magnet. Steel is difficult to magnetize and demagnetize and is used as a permanent magnet. We can confirm this because there are 5 iron nails attracted to the magnet and there are only 4 steel paper clips. And when we want to take the nails off, it's going to be easier to take these off than this. This shows that it's difficult to demagnetize the steel clips. So a magnetic field is the region around a magnet where a magnetic force can be felt. Magnetic field lines are represented by a straight line and arrowheads on the top. The direction of the magnetic field is always from north to south. Properties of magnetic field lines are that they start from north and end on the south pole. They never intersect with each other. They're always in a state of tension. The field lines repel each other sideways. The closeness of the field line indicate the strength of the magnetic field. So this is what the magnetic field line looks in a bar magnet. As you can see, it's traveling from north to south. Now, this is between two unlike poles on different magnets. The magnetic field lines are traveling from north to south again. These are two like poles, and they are repelling each other. They're not intersecting each other at all, and the point in the middle is usually known as the neutral point. The same can be said if the two poles were south. So to draw a magnetic field, we put a magnet and iron filings on a piece of paper, and the iron filings themselves will move into this shape. This is going to be the shape of the magnetic field. By using a plotting compass, so we take a magnet, we put a plotting compass from the North Pole, we draw a point here, then we put the compass on this point, and whatever direction the arrowhead points on you're going to draw the next point on it, and you're going to repeat this process, and you'll see that when you connect all the dots, it's going to reach the South Pole. So in electromagnetisation, the soft iron core is inserted into the solenoid. When the switch is closed, the electromagnet becomes very strong because the current is passing through it, and it loses all of its magnetism when the switch is opened. And this is especially used in magnetic relay, reed switches, electric bells, circuit breakers, loudspeakers, voltmeters, and ammeters. So in a magnetic relay, we turn the circuit on, meaning that a current is passing through it. When the current is passing through it, the magnetic material becomes an electromagnet. The iron armature will be attracted to the electromagnet, so it's going to move towards this electromagnet, and about the pivot, this is going to push this switch together. So when this switch is going to be connected, the second circuit will turn on. This is how a magnetic relay works. In a loudspeaker, when we turn the current on, it produces a magnetic field. As this coil is placed between the poles of a permanent magnet, the coil will experience a force. Since the cone is attached to the coil, it will also vibrate to and fro. This will produce sound waves. So the magnetic field around a straight current carrying wire. So when there's a cross in the diagram, it means that current is passing into the paper or medium, and when it's a dot, it means that it's passing out of a medium. So magnetic field around a current carrying wire is in the form of concentric circles, and to find the direction of the field lines, we use the right hand grip rule. This is also the same thing. So the current is going to be passing in through here and out through here. So since the current is passing in, we point our fingers upwards, and our finger is going to be extended on this side, and the current is going to be passing downwards here. So we take the fingers of our right hand and point it towards the direction of the current, and our extended thumb will point towards the direction of the North Pole. The magnetic field in a solenoid. So these crosses and circles show where the current is entering and leaving from. So it's entering from the circle and it's leaving from the cross. The field lines are going to be traveling from north to south, and inside the solenoid, the field lines are going to be in a state of tension. This is the end of the chapter.